So up until now, we used this return ratio and the asymptotic formula for gain. And then also we saw that it led to, naturally, the same framework led to Blackman's formula, which is very useful for impedance calculation. Return ratio seems to be a very useful thing, but there is something about it that now it has also weaknesses. And we'll talk about those also a little bit more later. But one of the challenges with return ratio, there are a couple of challenges with return ratio. First of all is that you need to access that source. You need to be able to access that source exactly to be able to calculate and evaluate it. And the other thing that we saw is that the return ratio is a function of what source we choose. So if you choose a different source, the return ratio will come out to be, it is not necessarily the same. Neither is the asymptotic gain, h infinity. Of course, the product of the three, I mean, that total overall calculation, as long as it's done for the same source, it would be always correct. But it's not an invariant of the loop in the sense that it doesn't change. It's something that would depend on which source you calculate. There's another problem with return ratio. So return ratio is a very useful thing. We use it a lot, don't take me wrong. But there's another problem, but it's not an invariant of the loop. And the other thing is that you need to have access to that source and say, what do you mean by that? Well, in the circuit diagrams that we draw on the whiteboard, there's not a problem because you can see them and you can access them. But for example, if you're in the circuit simulators, a lot of times you're actually using compact models for transistors. So these transistor models have a lot of parasitic capacitors and inductors and, well, often not inductors, but resistances and capacitors that are attached. So if you actually attach the external terminals of the device, you're not really necessarily where the actual dependent source is. So there are some intervening elements. And that can introduce some error in your calculation of return ratio. So accessing those sources is hard. Also, it's not an invariant of the loop. And that brings us to another quantity that we talk about and we use extensively, which is called the loop gain. And we'll see when they are the same and when they are different. So what do we mean by loop gain? Now, let's start thinking about a very idealized feedback loop first. I mean idealized in the sense that these are not even voltages and current necessarily. This is the kind of system level feedback loop that we talk about. So these are abstract signals, not necessarily voltages and currents, which basically means that there's no question of impedances involved here first. And we'll get to the impedances and see what they do. So if I look at a loop like this is the way a lot of control theory books draw a feedback loop, right? If you look at this, and if you say, okay, if I break this loop, if I break the loop, make a cut here, what would I see in the absence of an input? So x is 0. In the absence of an input, if I launch something, some u of x, what would I measure here as u of y? Right? This is an abstract loop. What do you see if I cut it there? If I launch u of x, of course, this would be u of x. Right? So this would be f times u of x. If this is 0, so this becomes negative f u of x. And then this becomes negative af u of x. Right? So if I look at this quantity, now, to differentiate between loop gain and return ratio, we use this t with two vertical lines to show the loop gain. But when you see something with this, I mean the loop gain. And when I see a single t, I mean the return ratio. So we are defining this thing as the ratio of uy over ux. And in this case, it would be af. Now, you say, why negative? Because what came back is minus. And this is correct. It already has a minus sign. So this is actually, again, a misnomer, really. This t is the negative of the loop gain, not the loop gain itself. But everyone calls this a loop gain. Same thing is true about return ratio. Return ratio is something we called that. But there's this minus sign to make this a positive thing. So it would be a positive quantity in a negative feedback loop because there's this extra minus sign. And if it becomes a negative quantity, it means that it's a positive feedback loop. Now, we can get into why they did that and should we still do this or not. But since everyone does it this way, we'll do it that way too. It's not a big deal as long as you understand there's a minus sign that corresponds to that. So if I break it here, obviously, we get this loop. Okay. Now, let's see, if I break it somewhere else, let's say, for example, if we broke it here instead of there, what would you get here? So if this is u of x, then this is going to be negative u of x. This is going to be negative a u of x, right? And what comes back here, so that's closed now, it's going to be negative af u of x. And in fact, you can see that if you had such a simple loop, simple and single, it was not a slip of the tongue. If you had such a loop, no matter where you break it, you will get the same quantity. So at least in this picture, this is an invariant of a loop. It doesn't matter where you calculate it. We saw that in general, this is not true about the return ratio. It depends on which sources you use and what kind of values you use. So this is a useful thing. This is an important thing, especially when we talk about stability. Because you want to have something that characterizes the loop entirely and completely that you can use as a metric for your stability. And that's why we go through the kind of like the process of getting this loop gain correctly and evaluating it accurately and things of that. So that is what we have in an idealized loop. Of course, in this picture, these guys are unilateral, meaning that the signal flows only in this direction in A and only in this direction in F. There's no forward transfer. And the way, if you draw it this way, there's no way for it to transfer forward anyway. Right? Now, if we become a little bit more realistic in terms of a circuit, so let's say you have an amplifier, let's say a voltage amplifier. So this is a slightly different way of thinking about it. That has an input impedance, and it has an output impedance too. So I call these Z1 and Z2. So let's say there's a voltage source, and this is Z1, and this is Z2. And then now you have a feedback network that has two impedances again, Z3 and Z4. So this is Z3, this is Z4, this is another feedback. So it's F times whatever, V2. Or V4, I guess. Or V out, let's call this V out. VO, and let's call this VI. Right? So this is A times VI, and this is F times VO. Now you can see this even in this picture, the way we've drawn it, this circuit is a unilateral feedback loop, right? Because both the feedback and the amplifier are unilateral. If I apply a signal here just to the amplifier on this end, nothing will appear here because there's no reverse dependent source. If I wanted to make it bilateral, I had to have another dependent source on this side. And the feedback network the same way. The signal from this side can appear on this side, but if I have a signal on this side by itself, it cannot induce anything here if it was not connected to something else. So this is a unilateral loop. Yes. Oh, sorry. So now if you break this unilateral loop, how can we break this now that we have impedances involved? If I just go ahead and break it like this, so let's say we make a cut here. And can I just do that and say, okay, I apply a VI here, and, or did we call it whatever we call it, Vx, and then measure Vy that comes back in the absence of an input. Is this correct? Do you see a problem with doing this? Did I change something as a result of doing this? If I just cut it, went in the lab and just took a pair of pliers or scissors or something like that and cut that loop, would everything remain the same, or things get messed up a little bit? Because now I've removed this impedance that was loading this guy, right? Excuse me. So what if I wanted to take its effect into account? What should I have done? does it make sense to say, look, you know what? This guy was loading this. So if I want to see what voltage it would have induced, I should probably put this Z4 here, right? And see what it does with that Z4. And then I say, OK, my Vx is really a voltage source. You can think about it as Vx. And I said, OK, well, this is good because now by substitution, this one is driving what it was driving before. So here, whatever voltage is, I'm inducing it here. So this other Z4 sees the same voltage. So the rest of the loop is not perturbed if I do that. So it sounds like I should be doing something like this, putting that impedance there to calculate this loop gain. And if I do that, then we can actually calculate what this gain is, right? So we can calculate what the loop gain looks like, right? So if I apply Vx here, this voltage is going to be so this is going to be now Vx, because that's the voltage that it depends on. So this is going to be Fvx. Now Fvx goes into these two impedances in series, right? You can do whatever you want with them. You can actually have them as some sort of a combination. And then it will come back here and it will go through the system, right? So you will have something like this and you can calculate the gain. And we can do it. But this is kind of an inconvenient thing, right? If you try to do that just like that. Another way to think about it, so another picture that represents this is that, of course, there are Thevenin and Norton equivalents. So this is a picture that we draw for analyzing this. This is not the way for understanding what happens, not for necessarily the way we analyze circuits. A lot of people actually use these like two-port methods for analyzing circuits. We are just using it for understanding what's going on. So you can think about it also another way. So this is another variation of that. So you have a dependent current source, and then you have a dependent current source here. And then you are basically taking these and creating a feedback network. So this goes here, and this goes here. And these things we call Y1, Y2. The way I've drawn it is just like this. So G3, this is Y3, Y1, Y2, Y4, and G1. So this is G1 VI, so this is VI, Vin, and this is VO. So if you write it this way, you can easily see that if you break the loop, and then you can have an I in if you want. If you break the loop and you calculate this with putting the right impedance in the right place, then you see that the unilateral gain which is defined as what comes back, uy versus u over ux, is going to be negative g1, g3 over yi, yo. And yi is the sum of the input impedances, admittances, sorry, and yo is the sum of the output admittances. So this would be the unilateral loop gain. The question is that, okay, so this is fine for this kind of network, but how do we calculate it for a realistic circuit, with impedances? And we can actually relatively easily show that we can, and I'm going to show it to you in a second, that you can actually calculate it several different ways. You can actually try to do this. You can try to anticipate what the load is and put it there. But sometimes when you have a complex transistors network, circuit, it becomes complicated. It's not as straightforward to know what that load is. And it kind of like feels a little bit redundant. Or you could say, you know what if I just did break it the way we described it? What if I just broke it and induced only a voltage source? What if I broke this loop? Let's break this loop here, somewhere, doesn't matter really, and say, look, you know what? I'm just going to apply a voltage to this. So we are going to apply a Vx, a voltage of Vx here without taking the loop into account, the loading into account, and monitor what comes out Vy. Right? We could do that. I mean, it's not necessarily the right thing because we are now ignoring that loading effect. Okay? But we can do it, right? So we can see what we get. If we do this, this is what we call a voltage loop gain, which would be defined as negative Vy over Vx. Remember, this time we are not taking the loading into account. We say, I'm going to cut the loop, and I'm just going to apply a voltage, and I don't care what it does to the rest of the circuit. It's going to mess it up. I don't care. I'm going to calculate what the loop gain is. And if you do that in this example, in this circuit, it would become negative, I mean, it's very easy to verify, G2, G3, YO, Y, I think 3. I'm saying YI, Y, so it becomes YI, Y2. I mean, it's very easy. Just apply this voltage. This voltage becomes G3Vx, and then you go through this calculation. This is null, so this is 0. So that's the input, and this would induce a voltage here that would produce that voltage at the output. It's just a very simple straight line. There's no feedback, right? We've broken the loop when you do that. So you get this quantity. You could also do the opposite. So you can say, but clearly this is not the same as this quantity, right? You said this is the loop gain. This is the unilateral loop gain. If we took the loading into account, this is the correct one. So you can clearly see that this is not the correct answer, because this is YO and this is Y2. So you can see that if you don't take the loading into account, it's not accurate. You can also do something else. You can say, you know what? I could also do something else. Instead of applying a voltage source here and keeping the other terminal open and looking at its voltage, I could do the opposite. We could apply a current source, Ix, okay, and short circuit the output and measure Iy. So we had one case where you apply a voltage source and you open circuit, measure the output of voltage, and then the other case where you actually short circuit the output and measure Iy. This is the current that would have flown into this port if it were shorted. Now, if you do that, that gives you what we call the current loop gain. And the current loop gain, which is defined as ratio of Iy over Ix, when this is shorted, of course, when Vy is 0. And that first one, if you want to be more precise about it, is that when Iy is 0, because that's open circuit, this is short circuit here, is going to be negative G2, G3, Yi, Y4, which is not equal to the unilateral loop gain either. But the key result is that if you look at these two carefully, you will see that this relationship actually holds. Oh, well, maybe I can keep the color code. For unilateral. And then there's a modification to this. There's a correction to this for bilateral. And the correction is not large, actually, depending on how much, of course, reverse gain you have, but typically it's not. So what you see here is that the interesting thing is that it says you can calculate your unilateral loop gain if you calculate your current loop gain and voltage loop gain independently, and you don't have to worry about the loading. You don't have to worry about what the loading was for this port and that port. You can break the loop anywhere you want, as long as you do these two calculations. There are two calculations, but you don't have to worry about anything else. And it says that for a single loop and unilateral loop, this should be valid no matter where you do it. So this is an important expression. And you will see that if you have bilateral, when you have bilateral loop, okay, basically meaning that signal can travel in both directions, there will be a third term added to these two that's a correction term. So it's these two plus a third term that we will find out. We'll talk about later. But let's see if this is really true. Let's look at an example and see how it applies. So the example, again, is one of the circuits that we've looked at before. So we have this guy, and then we have M1 and M2, so that's R2 and R1. R2, R1 to ground. This is your input voltage, V in. This is your output, V out. This is going to. So this is a circuit we've seen before, right? This is series in the input, if you want to think about it, and shunt in the output. It's a voltage in that terminology. But OK. So what is the loop? So this is M1 and M2. M1, M2. So we want to calculate loop gain, right? We have to break the loop somewhere. Where do we break it? Where should we break it? Well, let's break it at different places, see what happens. Let's break it here first. Or, well, let's break it here first. So we are breaking that loop here. So we need to calculate two quantities, the voltage loop gain and current loop gain, right? The voltage loop gain. If we apply voltage Vx, what do we get? Well, if it's Vx here, this current is going to be Gm2Vx, right, from a small signal perspective. That current is flowing through R1, so this voltage is going to be negative Gm2 R1Vx, right? And now that voltage is basically reflected here with a gain of this stage, which is going to be now Gm1 R3. Is that correct? Actually, this is not correct, what I wrote here. You know why? Why is this not correct? Isn't? Yes, and then this is Rm. So the total resistance on this node is R1 parallel Rm1, right? So Gm, this current, is going through the parallel combination of R1 parallel Rm1. So that's that voltage times Vx. And now that is the voltage here. And that voltage appears across Rm1 to produce this current, which goes through R3. So you get so this voltage would be Gm, so let's write it. Did I miss my color code? No, it's OK. TV is going to be what? This voltage is going to be Gm1 R3, Gm2 R1 parallel Rm1. Is that clear? Why it is the case? So that's what we get if we basically break the loop there for voltage loop gain. We have to do a second calculation, right? We have to do a current loop gain. So what is the current loop gain in this case? Well, for current loop gain, what you do, you apply a current source here, Ix, and short circuit here and measure Iy. Right? So what is the current loop gain? If I put a current Ix into the gate of a MOSFET at low frequencies, what am I going to get? What's the impedance of the gate? Infinity at low frequencies, right? So Ix going into infinity, what voltage would it generate? Infinity, right? So current into an infinite impedance. This would produce an infinity. Of course, it's small signal still, from a linearized model perspective. Infinity goes through, infinity comes back. So what is the current loop gain? defined as Iy over Ix when Vy is 0 is infinity. That's okay, because the equation we have, it says 1 over t total, or forward, is 1 over the loop gain, the voltage loop gain, plus 1 over the current loop gain. So this one goes to 0. And therefore, in this case, according to this, our loop gain is the voltage loop gain that we calculated, which is whatever, GM1, GM3, R3, R1 parallel RM. So that's one calculation. Now, we wanted to see, let's take this and then break the loop in somewhere else, so at some other location. So I'm just going to redraw the circuit very quickly. Okay, so R3, R2, R1, M1 and M2. So now let's break the loop somewhere else. Let's break it at some other location. Let's break it here. So what if we break the loop here? Again, we have to do two calculations: the voltage loop gain and current loop gain. So the voltage loop gain for this new location, so we can actually give them indexes, like indices. So this is going to be location 1, this is location 2. Okay. So this is a new one. This is a new calculation. It's not necessarily the same as this guy. Because the voltage loop gain, you said, it can be anything, or the current loop gain can be anything. Neither one of them are invariants of the loop by themselves. But that combination is, we claim at least. So let's see. TV, the new voltage loop gain. Apply a voltage source here, Vx, and measure Vy, right? So if you apply Vx here, it falls all across RM1. So you get a current which is basically GM1 Vx going through R3. So you have a GM1. Then you go through R3 to produce this voltage. Then you go through here, and then you have a GM2 to produce this current. But that GM2 goes only, the fraction that goes through R1 will produce the voltage. So that current is going to be going through here, but this part of it doesn't produce any voltage. This is that matters to us. This part of it is the part that goes. That current through R1 is what's going to happen, what's going to matter, right? So that's the voltage loop gain. And you can see it's not the same as before, because we broke it at a different place, which implies probably to us, if that our assumptions were correct, that the current loop gain should be non-infinity, should be finite. So let's calculate the current loop gain. So for the current loop gain, what we do, we get rid of this, and then we put a current source here, Ix, inject Ix, and short circuit and measure Iy. Okay, so if you put Ix through here, Ix is going to go through here, right? The gain for that transistor is 1, low frequency. So this is Ix. So this voltage is going to become Ix times R3. So there's an R3 there, right? And then that voltage would go through this guy, would give you a GM2, and that would produce this current. Now, this current would be flowing through here, and all of it will flow through here, through this short circuit, because the short will absorb all of the current that would be going through here. So that current, GM3R3, would go through Iy, through this short, which would be the Iy. Is it clear? Does it make sense? So that's the current loop gain. So now let's see what it is that if we calculate 1 over T V plus 1 over Ti, what do we get? Well, you get 1 over GM2 R3 GM1 R1 plus 1 over GM2 R3, And you can clearly factor this term out of both of them. So you get 1 over gm2r3 times 1 plus 1 over gm1r1, which you can and modify to become 1 over gm2r3. Then that becomes gm1 or 1 plus gm1r1 over gm1r1. So this is 1 over t. So the loop gain then is going to be 1 over that, which becomes gm2r3 times these guys. Now, which is basically gm1r1 over 1 plus gm1r1, right? If I multiply the numerator and denominator of this thing by rm1, what happens? What do we get?
R1 over R1 plus R1.
Yeah. No, not R1. Yeah, sorry. Yeah, correct. Now, I could also multiply by another gm1 and put an rm1 here, right? So now this is the parallel combination. So now you can see this is now equal to this guy. So it came out to be the same thing. And for good measures, let's do it. Let's cut the loop in the third place. Oh, not that way. This way. R2, R1. And this is ground. So now let's assume for the third cutting of the loop, let's cut it here. And let's just ignore the RO of the transistor. So now what is the voltage loop gain here? If I apply voltage here, Vx, and measure Vy. What is that voltage? What is that return? So whatever it goes through, something goes through here, something comes through here, something goes through here, but then it's driving an infinite impedance. I'm ignoring RO, right? If I'm driving infinite impedance, the voltage loop gain is going to be now infinity. So the loop, in this example, the voltage loop gain is infinity. I mean, I should say really goes to infinity, but very large. Notationally to be a little bit more accurate. But again, so that's that. And then how about the current loop gain? So if I apply a current here, if we apply an Ix and short circuit and measure Iy, okay, so Ix goes through here, so we are doing the I, it gives you an R3 there, then you get a GM2 here to generate that current. Then you have this current being split between these two branches, right? This is RM1. So you have a current divider between R1 and RM1 plus and RM1. So that's the current that goes through there. And again, you can see obviously that, so in this case, it says that the loop gain, total loop gain is going to be just the current loop gain because this is infinity. And again, you can multiply by GM1 RM1, which gives you the same expression. You can write it as GM1, GM2, R3, RM1 parallel R1, which is the same again. So what's the point of this thing? First of all, we demonstrated that this is true. I mean, well, as an example, it doesn't prove anything. But it shows you that if you use this equation, this expression for the unilateral loop gain at least, you can calculate the voltage loop gain and current loop gain independently, and you don't have to worry about the loading, which is a big thing, because actually a lot of these things, a lot of times in reality, this loop loading calculations are a mess. You don't need to do any of that. You just calculate these two with a short and an open at the output, respectively, well, with an open and a short, the output respectively. And then you use this expression to find the overall loop gain. And you can see that for a single loop, this is actually now invariant. Now, the situation can become a lot more interesting if you have multiple compounded loops and things of that sort. And there are a lot of things that can be said about that stuff. Then there are loops, there are nested loops, and then there are also kind of like, you can actually have crossing loops that are like, they're intercrossed, just like there are multiple things. And there are certain ways of dealing with that. Some of it boils down to Mason's formula and things of that sort. So now what we'll do next is that we have this is a powerful tool, but then we will also generalize it. And we see that if you have bilateral loop, meaning that the loop in which the signal can flow, for example, both clockwise and counterclockwise, what would happen? And you will see that there's a third correction term. In fact, I can tell you what it is now. So that third correction term is the reverse loop gain for one of the quantities, so reverse I, divided by the forward V, or vice versa. So there would be a third correction term of this nature, which we'll talk about next. Any questions on this?